So let's talk about Lambda. So some of you, if you've been to Java 1 before or other major conferences, you've seen presentations on our progress towards adding Lambda expressions to the Java language. This is the latest installment and such. So because Java 8 is coming into the home stretch, but not yet shipping. Hopefully, it'll be shipping this time next year, summer 2013. So we've titled this year's installment "The Road to Lambda," and in addition to talking about the features, programming language, and library features for Java 8, we're also going to talk a little bit about the history and some of the decisions that brought us to where we are here. Obligatory legal slide. There'll be a quiz on this at the end. Okay, so let's talk about why are we doing this at all? One of the questions that Mark asked yesterday at the keynote is, aren't collections and for loops good enough? We've been doing it this way for 17 years. It can't be that bad, right? And that's true. Java is Turing complete. You can write any program that's worth writing in Java, but it's possible to make it a little bit more pleasant, more fun, more powerful, more expressive, more readable, less error-prone, etc. And that's why we go through the effort of continuing to improve the language and the libraries. So Java 8 is going to be a big step forward in the programming model. There's a coordinated set of language improvements and library improvements. So the language improvements include Lambda expressions or closures, and also a mechanism for evolving interfaces compatibly over time. The library features include some big improvements to the collections for bulk data operations and parallel operations on collections, and increased library support for parallelism. And these features all work together. The language features that we're adding are in aid of being able to implement the library features we want. And together, these are a pretty big, should be a pretty big upgrade to the programming model. I've been programming with this stuff now for the last 6 months, and I have to say I really like it, and I think you're all going to like it as well. An obvious comparison for the work we're doing now is the work we did with generics in Java 5. That was also a pretty big change. That was a change to language and libraries as well. And just as generics enable us to better abstract over types, the goal of Lambda is to enable us to better abstract over behavior. And as I mentioned yesterday, how many people here were at the keynote yesterday? A lot, okay. The name for Lambda expressions is kind of a funny one. It's one that actually predates the dawn of computing. It goes back to the 30s in Alonzo Church's work on the foundations of the theory of computation. For some reason, in the last 80 years, we haven't come up with a better name, so the name stuck. We call them Lambda expressions. All right, so what is a Lambda expression? A Lambda expression is simply an anonymous method. Like a method, it has an argument list, it has parameters, it has a return type, has a set of thrown exceptions, has a body. So it has all the things a method has except a name. And it's not a member of a class, it's just a free-floating expression. So here's an example of a very simple Lambda expression that takes as its argument an object and whose body turns around, calls object.toString, and returns that. You'll notice a lot of the syntactic overhead of methods have been compressed away. There's no return statement. There's no braces. It's just an expression. And this expression, like inner classes, can refer to names from the enclosing scope. So in the second example, Lambda here that takes a person, turns around and calls p.getName and compares it to the name variable. Name variable is defined from outside of the Lambda. So whatever value name has outside of the Lambda, it has inside of the Lambda. A complementary feature that we're adding for Lambda expressions is method references, which behaves just like a Lambda expression, but if you already have a method, you just want to represent that method's behavior as an expression, you can refer to the method directly. So this method reference here, object.toString, is identical in behavior to the first Lambda we see. They both mean the same thing. Take your argument and pass it to object.toString. So why do we do this? The reason we do this is we want to be able to treat code as data. We want to be able to take behavior, stick it in a variable, pass it to a method, treat it as something that can be passed around rather than a fundamental property of a class. So this may not seem like a big deal. Like, after all we've done is like taken away a method's name. What's the big deal? But in reality, this is a huge deal. It's just going to change the way we program in a pretty fundamental way, and it has a huge impact on the way we design libraries. So, brief history lesson. So in 1995, when Java was invented, most popular programming languages at the time did not support closures. At the time, it was believed that closures were too complicated a concept for ordinary programmers, and a productive language didn't need closures, and that was the trends of the time. Things have changed. Today, Java is probably the last mainstream programming language that doesn't have closures. Even C++ added them recently after how many years of spec committee wrangling? 11 years, something like that. C# added them in version 3.0 as part of their link upgrade. Any credible new language being designed today, it's just a given, right? There's a nice quote here from Mark Jason Dominus, who's one of the architects of Perl, basically saying, at some point in the future, not having closures, it's going to be like not having recursion. It's just table stakes at this point. Okay. So the relationship between Java and closures has been a little bit of a colorful history. In 1997, there was some experimental work done by Phil Wadler and Martin Odersky that went into a prototype called Pizza that was added closures among other features to Java. In Java 1.1, we added inner classes, which was an attempt to get some of these benefits. They're a fairly weak form of closures. They have a lot of syntactic bulk. They have a lot of complexity and baggage and limitations, especially given the way they're implemented. So fast forwarding to about 6-7 years ago, there was a pretty vigorous debate in the Java community, first over whether there should be closures in Java, and then between multiple competing proposals about how to add closures to Java. So if anybody remembers the closure wars of those days, there was a proposal called BGGA, championed by Neil Gafter, and a proposal called CICE, championed by Josh Block. And what's interesting is they both had the same goal. Or they both had the same high-order bit goal, but they actually had very different approaches for what they thought adding closures to Java meant. And it's a lot like the old story about the blind man and the elephant, right? Everybody has hold of a different part of the elephant, and they each have an idea of what closures in Java should mean. And that's there are a lot of different aspects of it, and different people think different ones are more important. So BGGA was largely focused on adding control abstraction through libraries, whereas CICE was mostly focused on, let's just make the syntax for inner classes better and call it a day. So things never really converged here, and there was a sort of long period where really there was no discussion on the topic. And then in December 2009, Sun announced that, okay, we're finally going to do it. We picked a nice middle-of-the-road position between the extremes of some of the proposals that had been suggested. In November 2010, we formed a JSR after we had been working on the design for about a year in the context of OpenJDK. And the current status is actually getting fairly close to completion. We've done 2 early draft review specifications that are available publicly. There's a prototype available in OpenJDK, both source and binary, available for download. And this is going to be part of Java SE8, which hopefully is shipping in about a year. So the features that we're adding here: Lambda Expressions, interface evolution support in the form of default methods, and bulk operations on collections. All right, so let's take a look at some of the features. By way of background, let's look at how we do things today. Sorry to repeat the same examples I did yesterday, but there's a little bit. I have a little more time. I can spend a little more time talking about them. So here's an example of how we code every day in Java. You have a collection of things. You want to operate on some subset of those things, so you loop over the elements. You pick out the ones you want, and then you do something for each of them. So in this example, you have a collection of shapes. You pick out the red shapes, and you color them blue. And this is how we do it today. It's really the only tool we have for doing it today, but it sucks. And I can't criticize people for programming with this because it's the only tool we have for iterating over a collection. But it's a very limited and limiting way of dealing with aggregates. And the reason is the semantics of the for loop, as burned into the language, are very strict. They're strictly sequential. You have to do the first element first, and then you can't start the second element until you finish the first element, etc. And this is something that didn't cost anything to specify this way 20 years ago when all systems were single processor systems. But today, we're giving up a lot of potential performance. We're giving up opportunity to use parallelism, to use out-of-order execution, to exploit locality. So the for loop is really pretty heavily overspecified for today's hardware. At the same time, there's a lot of accidental complexity under the hood that you don't see because it's all covered by the syntactic sugar of the for each loop. So what the for each loop does is it expands out to ask the collection for an iterator, and then each time through the loop, ask it if it has any more elements, and if it does, ask it for the next element, and keep going. And how many people here have ever had to write an iterator? Right? Is it harder than it should be? Right? It's like it should be so easy, right? And you start writing it and you say, oh, I must be dumb. I'm getting this wrong. There's a lot of complexity to it. You end up duplicating a lot of code between next and has next. There's a lot of accidental complexity here. And you don't see it from the client side, but it introduces not only a complicated mechanism so that the client can drive the iteration, but also it's inherently racy because control is switching back and forth between the client and the collection and the client and the collection. All right. So this is the tool we had. It's called external iteration. The client drives the iteration. But it's not really a good match for today's hardware. And it's not really a good match for how we really would like to program. But it's a workaround for the fact that we couldn't do what we wanted to do, which was to hand a bit of behavior to the collection and say, do this for every element, you figure out how. So, what's being conflated in the for each loop example is the what do I want to do, test each shape to see if it's red and then color it blue, with the how do I do it? Get an iterator, take the first one, etc. And we would like to move the responsibility for the how fully into the library and leave the client in control of the what. Okay, because that frees up the library to use whatever bag of tricks it has at its disposal, parallelism, out-of-order execution, what have you, to get the right answer without bothering the client and the mechanics. So I've taken the example, I've rewritten this to use lambdas. It looks almost identical. It looks like it's just a syntactic reshuffling of the symbols, but the reality is, a lot has changed here because now the library is in control of the iteration. Here's a bit of behavior, do this for every element. We haven't specified in what order. We haven't specified what happens if there's an error. We haven't specified serial or parallel. Now, obviously, it's a fair amount of work to specify what the library's behavior should be in all these cases, but the client stays in charge of the what and leaves the how to the library, and that's a good thing. Another thing that you'll notice here in the Lambda syntax, I didn't have to write down the type of the argument s, the Lambda. The compiler just figures it out. It looks at the signature of for each, says for each takes a block. In this case, a block of shapes. So s must be a shape. The compiler just figures it out for you. It's not dynamic typing. It's just the compiler being smart and helping you out. So, like I said, this looks like a tiny syntactic change, so why are we making such a big fuss about it? Why is Oracle spending millions of dollars on this? Well, the reason is that this has a fundamental effect on the way we program, and in particular, it has a big effect on the kind of libraries that we can design. It has, it enables API designers. It gives them better tools for building libraries that are powerful, expressive, easy to use, etc., because they have more ability to abstract over behavior. Okay, so details. Expressions in Java have a type, so what is the type of a Lambda expression? So historically, the way we did things was we created libraries where we had these interfaces with one method, runnable, comparator, callable, etc. And so if you needed to pass behavior into a library, you passed one of these one-method interfaces. And that's been working pretty well for us. So we decided, let's just do that. We'll give it a name. We're going to call these special interfaces functional interfaces. You don't have to do anything special to declare them as a functional interface. They just are by virtue of having one method. And then we can say a Lambda expression, the type of a Lambda expression is a functional interface. So if I assign this Lambda expression to a predicate of string, the type of that expression is predicate of string. And the compiler uses the type information in the target to do type inference to figure out what the types of the Lambda formal variables are. If it can't figure it out, or you don't want to leave it unspecified, you can put explicit types there if you want. But a lot of the time, it's perfectly clear to just say, predicate of string is empty equals, string is empty. The nice thing here, by using this existing mechanism, which is the way we've been writing libraries for a long time, all of our existing libraries just work with this new language feature. So that's great. We didn't have to go write new libraries. If you have libraries that take things like, like the NIO libraries have like directory filters and things like that, you can just pass a Lambda in, as long as those are single method interfaces. Okay. So, the examples used a new method on collection that wasn't in collection. So that's kind of a problem. You're not supposed to be able to add methods to interfaces. And this has become more and more of a constraint over time as, as our collection library is going on 15 years old. The way we would write it today is not exactly the way we wrote it 15 years ago, but we're stuck with the way we wrote it 15 years ago. So we decided it's finally time to have a mechanism for evolving. I'll take questions at the end unless there's a technical problem. We decided it's finally time to let libraries evolve, with usage patterns, with language evolution, etc. Because otherwise, if libraries can't evolve, they just become brittle and eventually they become irrelevant. And then we would have to throw out our libraries and replace them every 5 years, which is very, very disruptive. So in order to let libraries evolve, we have a mechanism for evolving them. You can put code in interfaces using these what are called default methods. You say this is a default method, here's the body. In the event that the subtype doesn't provide an implementation, it uses the default implementation. So these are full virtual methods, just like any other interface method. And this is actually the code for collection.forEach. It's really simple. If a collection implementation wants to provide a better implementation, just override it. Okay, so so a default method lets you provide an implementation with the method declaration in the interface. So a lot of people look at this and say, oh my God, you're adding multiple inheritance to Java. And well, no, we're not, because Java always had multiple inheritance. Java always had multiple inheritance of types. A class can implement multiple interfaces. It can inherit from multiple interfaces. What we're adding is multiple inheritance of behavior. What we're not adding is multiple inheritance of state. And almost all the pain of multiple inheritance in languages like C++ comes from multiple inheritance of state. So this mechanism, it bears a sort of a superficial similarity to extension methods in C#. It's actually different in two key ways. Ours are virtual, theirs are static. Ours are declaration site, theirs are use site. It also bears some resemblance to stateless traits in languages like Fortran. It's not exactly traits in Scala. If you're a Scala programmer and you were hoping this is the traits you wanted, you'll be disappointed. But you'll find that you can use these as a very effective inheritance mechanism on their own, even though the primary reason we added this feature to the language was interface evolution. Okay, so let's see how they work. It's single inheritance, very simple, right? We've had no trouble reasoning about that. Multiple inheritance is a little bit more complicated, but there's a few basic rules so that you can reason about what supertype am I going to inherit my behavior from. So the first rule is a straightforward one. If the superclass has an implementation or has a declaration, the class wins. Don't even look at what the interfaces do. If the class has an implementation or it has an abstract declaration, that's what you inherit, done, end of story. Okay? In the event there's a conflict between two interfaces, if one of them is a subtype of another, the subtype wins. So if you have a for each method in collection and a for each method in list, because list is a subtype of collection, you inherit the one from the more specific type. And if we can't disambiguate by one of those two rules, then it's just as if the method was abstract and you have to provide an implementation. Okay? So you don't have to do an awful lot of reasoning about which one of these am I going to inherit. We try to manage the complexity of multiple inheritance by having some really simple rules for this. So the first question everyone asks is, when they hear multiple inheritance is, what about diamonds? Diamonds were a really nasty problem in C++, so that must be an inherent problem with multiple inheritance. Well, it turns out when you take state out of the equation, diamonds are easy. Okay, so in the top example here, I've got an interface A with a default method, and B and C both extend A, and D implements B and C. Well, there's only one method I can inherit from, right? I can inherit from A or A. I happen to have two different paths to it, but that's irrelevant. So D inherits its definition of M from A. If I modified the example a little bit by giving B a default implementation for M as well, then the rule about subclasses comes into play. B is a subclass of A, therefore B's takes precedence over A's. And again, D inherits the method from B, and there's no ambiguity. Even though D is implementing both B and C, and so it's indirectly implementing both A and B, B is a more specific type, B wins. The order in which they appear on the inheritance line is not relevant. Whether A appeared redundantly on the inherits line, not relevant. It's simply a matter of inheriting from the most specific interface. Okay, so this should be fairly simple to reason about. And in the case where you have two supertypes that both provide a default, well, you just have to provide an implementation on your own. So you override it as if it were an abstract method, and if you want to call back to one of the inherited implementations, there's a slight extension of the super syntax where you can say, instead of super.m, you can say a.super.m or b.super.m. So pretty straightforward. So why are we doing this? Well, like I said, we want to be able to evolve our APIs. The collection APIs haven't changed in a long time. When you add a feature like Lambda to the language, now they look even more out of date, right? Where's my for each method? Why can't I, for each over the elements of a collection and apply a Lambda to each one? Okay, so here are some examples of things that we're adding to collection. The first one's pretty obvious. For each method, you hand it a block. You apply the block for every element. And the second example, is that too small to read in the back? Can anybody read that? Raise your hand if you can read that. All right, looks like about the first 2/3 of the room can read that. The second method here is a remove if, and you pass it a predicate, which is you say to a collection, remove all the elements that match this predicate. Now, we had a remove all method the first time around, but you could only pass it an object. It was remove all the elements that are equal to this object. That was the best we could do without closures. But obviously, this is more powerful. This gives the client an opportunity to say, what? Remove all the elements that are blue, without having to manually iterate through them sequentially and do all the work itself. Okay? An interface can provide a default implementation that is weak. That's okay. Subclasses can provide better ones because these are virtual methods. So if you're an API maintainer, this is a very powerful mechanism for evolving your APIs as you go along. It's also a nice mechanism for just building better APIs. So coming back to iterator before, one of everybody's pet peeves with iterator is you have to implement has next, you have to implement next. Almost nobody ever implements remove, except you have to implement it with a body that says, throw some kind of exception. So if we have a default implementation that throws that exception, well, now if you're not looking to override that, you're not looking to provide a better implementation of remove, now you don't have to provide the implementation. That's kind of nice. It means that life is a little bit easier for the people implementing the classes that you've written. So, again, even though the mechanism was designed for API evolution, it's also a mechanism for making APIs better. So here are some really nice examples. These are really pretty examples. We have the interface comparator, which compares two objects to see if one is less than or equal or greater than the other. And common things that you might want to do with comparators are reverse the direction of the comparator, sort ascending versus descending, or take two comparators and compose them. So if you have a comparator for first name and a comparator for last name, you can compose them into sort by first and last name. So these are a pain to implement without lambdas, so people don't do it. But they're trivial to implement with lambdas, and so we can add them as extension methods or default methods onto comparator. So we added a reverse method to comparator. So if you have a comparator, you can say comparator.reverse. And it just reverses the direction of it. And the implementation is trivial. The implementation is, call the compare method with the objects in the opposite order. Similarly, we added a compose method to comparator. Compose this comparator with another comparator. And again, the implementation is trivial. Call the first comparator. If it's not 0, return that. Otherwise, call the second comparator and return that. Okay? So, if you have comparators for, say, first name and last name, you can make a you can make a descending comparator by calling the reverse on it. You can make a composite comparator that is by first and last just by saying by last dot compose by first. All right. So and that doesn't affect the fact that comparator is one of these single method interfaces because default methods don't count against your abstract method limit. Okay. So this is a really nice thing. It has nothing to do with interface evolution, but it's a really nice tool for library providers, to add things like predicate.and and such, as instance methods on. Okay, so let's talk about the what we're doing with the collection APIs, because I kept saying that Lambda is a tool for making better APIs. Well, let's see what we're going to do with collections. So I gave you this example earlier where I said, okay, shapes dot for each. Here's a lambda that selects out some of the shapes, ignores some of them, and acts on others. Really what we'd like to do is decompose that a little bit because there's two things going on, and things are always cleaner if you can break things down to their sort of most basic representation. Okay, so we can transform this from just do this for every element to take the collection and then filter the ones that meet this criteria, in this case being red, and then for each of those, apply this action to it, turn them blue. Okay? So this code isn't necessarily shorter than the previous code, but it's better. It's more expressive, it's cleaner, it's simpler. If you make small changes to the problem statement, you end up with small changes to the resulting code. You don't end up with changes rippling through the structure of the code just because you're doing something slightly different. Each part does one thing. That thing is clearly labeled. Plus, also, we've moved the control of the process into the library, who can then use parallelism, etc. Okay, so we can keep going with this. Let's say we're collecting, not just pick out the blocks that are blue, but okay, I skipped an example. So I have my shapes example. I say I want to collect the blue ones into an array. The way I used to do that is I create an empty array. I do my for loop. I do my test, and then the ones I pick, I stick them into the collection. A more declarative way to do it is to say, take the shapes, filter the ones that are blue, and stick those into this collection. Okay? And similarly, if I wanted to collect not the shapes, but some metadata about the shapes, let's say each shape is contained in a box, I wanted to collect the set of boxes that contain a blue shape. I can make a very small change. I've made a small change to the problem. I can make a small change to my code. I say, take my shapes, filter out the ones that are blue. For each that are left, replace that with the box that it contains and stick those into a set. Okay? And similarly, if I wanted to add up the sum of the weights of the blue blocks, take my shapes, filter them, filter the ones that are blue, replace each one of them with its weight, add those weights up. Okay? And I showed you earlier an alternate syntax for method references, perhaps a slightly more compact way to write this. Rather than having to write a lambda that all it does is go and call the getWeight method, I can just say map it using this mapping function. Okay? So this is a sort of more natural way to express collections when you have an easy, lightweight mechanism to pass behavior from the client into the library. Okay, so you know, I've said a few times, I'll say a few more times before I'm done, it may look like a small change, but it completely changes the character of the libraries we write. And I would much rather write this code than write the ad hoc code that we've always been writing. It's a lot clearer to me. It factors a lot more cleanly. There's no mutable state in the client. It's just a lot cleaner. Okay, so the key thing here is these operations are composable. I can compose these complex compound operations by stringing together simple basic building blocks where each block does one thing, and the net result is the client code ends up reading like the problem statement. Take the blue blocks, color them red, stick them into a collection. Also, one of the things that goes away when you program in this style is a lot of the extraneous noise from intermediate results, right? You know, so the old way you would say, you know, collection equals new collection, blah, 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 collection.add, and the declaration is in some sense extraneous, right? You end up declaring all these intermediate variables that just hold an intermediate result, and then you're going to throw them away. By restructuring the code like this, all of those intermediate variables get out of the way, and you could see what the code is doing. And again, you know, library can use parallelism, it can use out of order, it can use laziness, whatever it wants to use. Okay, so I mentioned laziness. What do I mean by laziness? Laziness is a measure of when the work actually happens. So when you call, you know, so if I say filter the elements of this collection, it's a valid question to ask, well, when does that filtering happen? And there's two choices. So an eager approach is do it immediately. By the time the method call returns, the filtering should have happened. The lazy approach is, well, do it at the last possible moment when somebody asks for the result. Okay? And a lot of operations, like filtering or mapping, can be implemented either way. And they have pros and cons of both. But you know, mechanisms like iterators that we've used, you know, for years for iterating through collections, those are inherently lazy. It doesn't have to know what the next element is until you call next. And so we're kind of used to the idea of working on elements one at a time and letting them be computed on the fly. And laziness can be a source of significant efficiency. If you're, for example, let's say you have a collection of 1 million elements and you want to say, get me the first one that matches this criteria. If everything was eager, you'd have to apply the criteria to 1 million elements, and maybe that was a lot of wasted work because the third element matched the criteria. So if you're doing the computation lazily, you're only doing the computation on enough elements to give you your answer. So as a mechanism for adding these bulk operations to collection, we've added a new abstraction to the collection library, which we're calling stream, and represents a stream of values. It's not a data structure, it's not a linked list, it's not an array list, it's just an abstraction for the values are flowing by and you can act on them. And you can use existing collections or arrays as a source for your stream. You can use existing collections as something to dump the results of a stream into, and the stuff in the middle is just computation. Operations that produce, you know, on streams that produce new streams, like filter and map, those are implemented as being lazy. So, you know, if you look at the signature, you know, of the filter method, it returns a new stream. So I've sort of written it out sort of in a more verbose way than we ordinarily would, which is assigning, you know, giving a variable to each of the intermediate elements in the calculation. Take the collection, turn it into a stream. Take that stream, filter it. Take that filtered stream, apply a mapping function to it. And at this point, no work has actually happened. We've just set up the calculation that we're going to do, and then when we say take the last thing, do it for each, apply this, this lambda to every element of the collection, that's when the work happens because now the user has asked for something. Now we wouldn't generally write it like this, we would normally write it more like this just to make it clearer, but I wrote the example out full so you could see what all the intermediate types were, to see that filter returns a new stream, it doesn't return a new collection. Okay? You know, this is, you know, this style of API writing. Sometimes it's called fluent. Some things that claim to be fluent are more and less fluent. But the idea here is you try to eliminate the noise of setting things up so that it reads like, first do this, then do this, then do this. Okay. So like I said, we have some operations that are lazy and some operations that are eager. The terms we actually use are intermediate and terminal, and so you can chain together as many intermediate operations as you want, and you're just setting up the calculation pipeline. And then when you do a terminal operation, that's when all the work happens, and that's when the library commits to how is it going to actually implement this. Is it going to get an iterator? Is it going to call for each? What have you. So let's see. Let's walk through the Stream API briefly. So there's the methods we've seen before: filter, map, flat map. Those are all intermediate operations. Some more complex intermediate operations: sorting, duplicate filtration, slicing the stream. Chop off all the elements after the 10th. Discard the elements up to the 100th, etc. And then some terminal operations for each. Do this for each element. Dump this into a collection. Turn it into an array. Aggregate by this aggregating function, like add them all up, or take the maximum, or what have you, or find the first one, find the find any element that you can find, etc. And even some more complicated things like group by. Take this classification function and produce me a map whose keys are the results of the classification function and whose values are the elements of the original collection. So this is a pretty rich API, and I'll just give you sort of one sort of more sophisticated example of what you can do with it. Let's say I've sort of written a problem statement out. I've written out in SQL because, after all, this is an Oracle conference, and there must be some SQL in every presentation. You have a collection of documents. Each document has an author. You want to add up the sum of all the pages of all the documents by author. So the old way to do that is you create a map, you iterate through all the documents, you get the author for each document, you look to see if there is something in the map for that author. If there's not, you have to put an initial element in, and then you replace it with the sum of what was there and the page count of the new one. This is pretty straightforward. Okay? This is how we would write it with the Streams API. We would use the aggregate by function, which is a little tricky to read, so I'll walk through it a little bit more slowly. I'm saying take the set of documents and aggregate them using the author as my classifier. So I'm going to whack the documents into bins where all the documents in one bin are by one author, all the documents in the next bin are by another author, etc. And then rather than just having a collection of documents by author, I'm going to aggregate across a bin. And the initial value for any bin is provided by the first lambda in blue, which is just return 0. So when you have no documents in a bin, the value associated with that author is 0. And then if you add a new document to that bin, you combine it using this combining function that takes the previous sum and the new document and adds the sum to the page count of the new document and replaces the value with that. So at the end of all of this, you have a map indexed by author of integers. Okay? You haven't created intermediate collections. You've just said, here's how I want to slice and dice things. I want to aggregate by this aggregating function. It's pretty powerful. It's a little, this isn't, it takes a while to learn to read these examples, but it's a lot clearer and cleaner once you do. Okay. So I talked about laziness. If you look at the kind of code that uses for loops today, because we're trying to replace as many for loops as possible with bulk operations on collections, it turns out that they correspond to these pipelines that are take a collection, do 0 or more of these intermediate operations, and then do one terminal operation. So take a collection, do some filtering, do some replacement, and then add up the elements. Take an array, apply a function to it, sort the results, and then print them out, etc. So you can think of streams as being lazy collections, but what we haven't done is added the complexity of new types for lazy list, lazy collection, lazy sorted, synchronized map, etc. Okay, all the laziness just sort of happens, and it's not explicit in the code, but it gets you the result you want. Okay. So the other thing that I talked about that moving the control of the computation into the library does is the library can use parallelism. And this has clearly been one of the goals from the outset. You know, one of Java's strengths has always been its libraries, and the best way, you know, to write better application is to have better libraries. And so if we want to make the Java platform more powerful, we want to encourage more powerful libraries. And specifically, parallelism is one of those things that we would like to not burden users with. So if we can hide all the details of parallelisms like task scheduling and load balancing and all of that in the libraries, we all win. It's hard to do. These libraries can be written by experts. You know, there's no reason why everyone should have to do that by themselves. So we have libraries for parallelism in the JDK now. We have the fork join library that we added in Java 7, which is a pretty powerful library, but it's really hard to use. How many people here have tried to use fork join? Okay, was it easy? How many people here think fork join is easy? Okay, few crazy guys like Charlie and me, and right. Okay, so what ends up happening then is writing the serial code is easy. Writing the parallel code is a pain in the ass. So try not to write the parallel code because we're all inherently lazy, right? So we end up not going parallel just because it's inconvenient. And you know, that means that our programs are not as efficient as we'd like them to be. Another problem with the fork join libraries is there's so much code to use them that the serial version of the code and the parallel version of the code don't look anything like each other. And it gets hard to see the forest for the trees. So we would like parallelism to still be explicit. We're not going to magically inject parallelism into your applications, but we'd like it to be unobtrusive. So fork join is based on recursive decomposition. The idea is you solve a big problem by chopping it into two smaller problems and then recursively chopping it into smaller and smaller problems until the problems are so small that the easiest thing to do is just solve the subproblems sequentially and then combine the results up the tree. And this tends to be pretty efficient, and fork join offers a pretty nice mechanism for writing those algorithms so that they work whether you have 1 core or 1,000 cores available to you. So fork join code typically looks something like this. Take the problem. If it's small enough, just solve it sequentially. Otherwise, whack it in two, solve the left and right halves in parallel, and then combine the results. So if your problem is pick the biggest element out of a collection, well, all right, you divide it in two, you pick the biggest element out of each subcollection, and then you take the biggest of those two, and that's your combiner. So the parallel sum example I had, you're not supposed to be able to read this, you know, a few slides ago, writing that with fork join looks something like this. And the stuff in red is the stuff that you'll recognize as the business logic of iterate through my collection, you know, pick out the ones I want, add up the sizes, etc. And the rest is all boilerplate to keep the framework happy. Okay, so I would much rather write it like this. Say, I want to do this pipeline of operations. I'm going to do a filter map reduce on this collection. I want to do it in parallel, but the parallel code and the serial code are almost identical. They're different enough so that there's no magic parallelism, but they're similar enough that you can look at it and immediately see what's this code doing. And by the way, it looks like we're doing 3 operations here. It looks like we're doing a filter and then a map and then a reduce. But because of laziness, we don't actually have to do them explicitly. The library will fuse these together into a single parallel pass. So it only touches the data once. That's pretty cool. Okay, so we don't actually have a separate abstraction for parallel stream. We just have streams. Streams can be serial or parallel. Which one they are depends on where they came from. Take a collection, give me a stream, that's sequential. Take me a collection, give me a parallel stream, that's parallel. Some data structures decompose better than others. Arrays decompose really nicely. Linked lists decompose really badly. But we abstract away the decomposition mechanism. We can try to apply whatever parallelism we can extract, subject to however well the collection can decompose itself. So we have an abstraction for decomposition where the parallel analog of iterator is splitterator. Right? Iterator serves up the elements one at a time. Splitterator recursively can decompose the collection into smaller splittable chunks. So you can say, I want to traverse this chunk sequentially, give me an iterator for it. I want to divide this chunk into smaller chunks. Let me split off a chunk. And then each, now I have 2 splitterators, and I could keep splitting, or I could decide to stop splitting, etc. Once you have a splitterator for a data structure, all of these parallel algorithms can apply on them. Obviously, if you have a lousy splitting approach, like a linked list, you're not going to get as much parallelism as if you have a much cleaner split, like an array. But at least we can execute these parallel operations on any data structure that knows how to split itself. Okay, so let me get to the good stuff here. So why are we doing this? We're doing this, for a lot of reasons. We're doing this because of parallelism. We're doing this because we're modernizing the language. But we also just want to make things better. And the reality is that having lambdas in your language makes it easier to build better libraries. And this is not new, right? We didn't just discover this last week. This community has known this for 50 years. We're not breaking new ground here. But the relationship between a client and a library really changes when you're able to pass behavior from the client to the library. It's not just, here's a bunch of data, go do something and let me know the result. I can pass bits of behavior of, do this, and then when this happens, call this function. And when that happens, call that function. And it makes for sort of a much more equal partnership between the library and the client. The client remains in control of the what, the library remains in control of the how. It's a much better factoring. So as an example, let's take a look at what this does to sorting APIs. So here's the old way. If you want to sort a list today, you write a comparator. Now, a comparator is actually conflating 2 different things that you want for sorting elements. One is extracting a sort key, and the other is comparing those sort keys. And we can factor those out. We could just replace the inner class with a lambda, but that doesn't actually get us very far. So instead, we're going to separate those 2 aspects out. Here's a method we added to the library. We have a class comparators. It's a static method called comparing. And this is the kind of thing that lambdas encourage you to do. The generics are a little nasty, but don't let that throw you, because what's going on is really simple. This is a function, comparing, that takes a function and returns a function. Okay? So the function that I pass in is extract my sort key. The generics nastiness just says make sure the sort key is comparable. Okay? And so I pass in a function that takes that let's say takes a person and returns last name. So it takes the thing you want to sort and it returns the sort key, and it returns you a comparator. Okay? So as long as the thing that the extractor returns is comparable, I pass in a function that, say, takes a person, returns a string, and then it returns me a comparator that compares that string using its natural compare-to ordering. Okay? Now, you don't have to write this method. We write this method. Okay? Then this is part of the libraries. It means that if you want to make a comparator of people sorting by last name, you can say comparators.comparing, take a person, return his last name, which is a lot closer to the actual problem you're trying to solve. All the details of actually writing a comparator, that's all accidental complexity. Okay, so this is an example of a higher order function. It takes a function in, returns a function out. The function in extracts the sort key. The function it returns is a comparator. Okay, so here's a simple way to use that. I want to sort the people by last name. So I say, give me a comparator that sorts person objects by last name. I pass it in a function that extracts the last name for a person. It returns me a comparator. I can say sort that. So that's already better than what we have today, but we can do better still. It's actually compact enough that I don't need the intermediate variable. I can say sort people comparing last name. All right, this is getting a lot closer to the problem statement. Because now we can add methods to interfaces. I can put the sort method where it belongs on the list and say people.sort comparing last name. And in fact, like, this lambda is kind of a silly lambda. All it does is turn around and call some other method. So why don't we just name the method directly using a method reference? And all of the goo of comparators is gone by adding one method to the library. Okay? And that method that we added, aside from its nasty generics, was a pretty simple one. Okay? If I want to sort people by last name backwards, I just take the comparator I got from comparing and call the reverse method on it. You saw the definition of reverse, 20 slides ago. It wasn't that nasty. If I want to sort by last name and then first name, I say, make me a comparator that compares last name, compose that with a comparator that compares first name, and sort by the combination. Okay? Having lambdas in the language makes it a lot easier to build APIs that look like this. And so that the user doesn't have to contribute all of the goo associated with sorting. They can just contribute the little bits that they want. Okay? This is a much nicer relationship between the client and the library. So we could have written this method with inner classes, but what would be the point? Right? No one would want to use it anyway. It would still be nasty. Okay? So having language in the library, having lambdas in the language lets you write APIs that are more composable. Okay? If we can write better libraries, we can write more readable and less error-prone user code. Okay? So that's the big picture. So there's a lot of reasons why we would rather evolve the programming model by libraries rather than language. Libraries are easier to write, they're cheaper to write, there's more people that can do it, it's decentralized. If you screw up, you can change libraries more easily than you can change the language. So we prefer to add language features that support libraries rather than support user code, because that's the rising tide that lifts all boats. Okay, so wrapping up, why are we doing this? Well, first of all, it's about time. All the other cool kids have done it already. Java is really the last, language of any serious adoption that doesn't already have closures. And adding lambdas to Java is no longer a radical idea. It was a radical idea 10 years ago. Times change. It's not anymore. Providing libraries a path to multicore, huge driver for this work. Parallel APIs need to have internal iteration. Internal iteration needs to have a code as data mechanism. That's what lambdas give you. Empower the library developers. That makes everybody's life better. Okay, so where are we now? Like I said, we have a spec available. We have an implementation available. And come hell or high water, it's shipping next year. And with that, I'm happy to take questions. Yeah?
I was wondering if some of the new methods on the collection interface could also have been added to the iterable.
Yeah, so the question is, why did you add things to collection, why not to iterable? So we explored that, and in fact, in an earlier version of the library design, that's what we did, which is exactly what Microsoft has done in their CLR libraries. They load all of the interesting methods into iterable. It turned out that was confusing for people. We ran some focus groups, and we found that people were confused about what that meant, because you had lazy methods mixed in with eager methods, because you had the lazy methods you're inheriting from iterable and the eager methods in the collection, and it was confusing the users. So we separated them out into a stream abstraction where you have the in-place methods on collection, you have a way of turning a collection into a stream, and the lazy methods on stream. It turned out to be less confusing. Let's let some other people ask questions.
My question is, since your Lambda expressions are first-class objects now, do you have methods, techniques for constructing Lambda expressions at runtime? Filter, map, reduce over and over and over again.
So, you've seen examples where you call a method, it returns a lambda. So obviously, if you just want to return a new function, you can do that. If you're talking about how it is that we implement that, do you want to not evaluate the lambda expression multiple times? Is that?
No, at the programming level, constructing Lambda expressions at runtime.
Yeah.
How does a programmer do that? Can you do that?
Oh, you want to do it reflectively?
Yes.
Not yet.
A follow-on question would be that it would seem to be a very, very hairy thing to try and do because of the generics involved in doing like.
Yeah, so one of the reasons why that's not there yet. More questions? There. Yes, you.
Can you tell me a bit about how these things are evaluated by the
Yeah, all right, so the question is, do these things get inlined by the JVM? So who here is a performance weenie? Raise your hand. All right, so you should all come to my talk tomorrow morning at 8:30, horribly early. If it makes you feel better, I have to get up earlier than you do. And I'm going to talk about the guts of how this is implemented in the VM. But very quickly, this is built on top of invoke dynamic and method handles. So for a lot of the common cases of Lambda, for example, like when you're not capturing anything from the local context, capturing a Lambda expression boils down into a constant load of a method handle that the VM then knows how to inline right through. So the capture cost in the common case are basically 0, and because this is built on method handles, the VM understands how to inline through these things. So we've been working very closely with the VM folks who did JSR 292 to make sure that this stuff is not only fun to program with, but fast. Yes, ma'am.
Maybe a stupid question. You had a slide about like splitterator.
Mm-hmm.
I was wondering if you already have parallel, why would you need to do that?
So the question is, why do we need this abstraction for splitterator? There it is, right? Because we've already added parallel operations, to the collections. Well, the reason is this is our mechanism for adding parallel operations. If you want to be able to do a parallel operation on a collection, it needs to provide a way of splitting itself. So all of the collections in the JDK implement their own splitterator, but if you have your own collection that you want to do parallel operations on, all you have to do is implement splitterator for that, and everything else comes for free. Yes, but the number of people who have to implement this is much smaller, right? So iterators are a pain to implement, but they're also not something that you should have to be doing all the time, right? The reason we end up having to use iterators all the time is because we didn't have a mechanism for internal iteration, right? So every collection had to provide a way of getting at the elements sequentially. And then we had to define all of these rules about interference of what happens if the collection is modified between calls to next and then has next, etc. All of that complexity goes away when the iteration is contained within the collection itself. So yes, some people are going to have to write this, mostly, Mike and Joe and Stuart and, guys on the libraries team. This is not an API that we could get away without even exposing this API, in the JDK. But this is, at the low level, how it is that we end up getting parallelism across all of the different collections. Over there, sir.
So this is all for A,
Correct.
correct? Nothing we can do except
So the question is,
it's coming in December.
right, this is all, so when can we have it and why can't we have it yesterday is the question. And so you can have it yesterday if you're willing to run with experimental, builds of OpenJDK, which you're absolutely welcome to do. Not only welcome to do, but please do. All right? The only way we're going to figure out whether we've done it right is if people download it now. If you wait until after 8 comes out, there's much less that we can do to change things. So the most valuable thing that people can do, if you're interested in this, is go download the binaries, try it out. If it works for you, post something to Lambda Dev saying, hey, I tried it and it was great. If it doesn't work for you, post bug reports. There's lots of people, who like to chatter about language design and library design on Lambda Dev, but the most valuable contributions we get from the community are the people who say, I tried it out and I ran into this bug. Those people are making far more of a contribution. So please, be one of those people. We had a question over there?
Would it be safe to use this in a maybe container or parallelism?
So certainly, Lambda expressions are part of the language, perfectly safe to do. I don't know about the parallelism. I don't know what the rules are. I know the rules for creating threads in EJB containers are complicated. So I'm not sure if it would actually be able to create the fork join pool that it needs. We'll have to work that out, but I suspect it will be. EE containers, want to exert more control over what computing resources you use. We haven't worked out the rules for that yet. Question here.
So with interfaces now getting default classes or default methods, it seems like the difference between an interface and an abstract class is getting a little gray. Is
Right.
the abstract class idea going to go away? Is it going to be deprecated?
Yeah, so the question is, now interfaces are looking more like abstract classes, so our abstract class is gone. And there's still a big difference. So you're right. The set of, so the style guidelines have always said, if you can get away with an interface, use that instead of an abstract class. The one thing that you can do with abstract classes now that you can't do with interfaces is have variables, right? So if you want to have state, you have to do an abstract class. But a lot of the things that we would have done with abstract classes today, we can do with interfaces tomorrow.
Except for variables.
What's the?
You can get multiple variables without them.
Right. So one of the disadvantages of using abstract classes is you still only get one class inheritance. So more of the things that you might have done with abstract classes, you can now do with interfaces. All right. One last question. Someone who hasn't asked before. Yes.
Has there been consideration to allowing one to declare a method, i.e. Java ref method constants via the syntax, and in particular allow those assignments to annotation values?
Yes. Okay. So the question is, wouldn't it be great if I could take that method reference syntax and assign it to a Java-lang method, and in fact, wouldn't it be even greater if I could put that in an annotation? And the question is, has there been any consideration given to that? And the answer is yes. There has been extensive consideration given to that. Anybody else? So the answer is not an 8, maybe a 9. Okay? We have been exceedingly careful to not get in the way of doing that in the future. But we have not committed to doing that now. Similar question, field references, same story. All right. Thank you very much, everybody.